In this course, we are going to consider significant figures, also known as significant digits. Now, it is tremendously important for us to use significant figures for two reasons. Our answer must consider the precision and uncertainty associated with your input measurements. Also, your answer signifies something that has to be measurable or producible. That is, if you give a machinist a drawing that has 10 decimal places, they would not be able to produce that. As per item 1, if someone provides you a measurement of 10 feet, you don't know the precision of this. Is it 10 feet 1 inches? Is it 10 feet and a quarter inch? And thus we have to develop a rule to signify the significance of 10. As per item 2, as you begin to increase the number of digits to the right of the decimal place, oftentimes the machining cost increases by a factor of 10 for each increment, and there are limits to what can be machined. For conventional machining, you can typically go down to a thousandth of an inch or 5/10thou. To go any higher, i.e. to be in the millionths of an inch, you have to use wire EDM and the like, which becomes very expensive. Now, we have 5 rules when considering significant figures, and they are as follows. Any non-zero number is a significant digit. That is, 1, 2, 3, 4, 5, 6, 7, 8, and 9 are all significant digits. And if we report a number of 99, this has 2 significant figures associated with it. On the previous slide, 10 would only have 1 significant figure associated with it. When a zero exists between 2 non-zero significant digits, itself becomes significant. That is, 101, or 1001, or 10,001 have 3, 4, and 5 significant digits respectively. The 0 in between the 1s are significant. Any 0 before a non-zero significant digit is not significant in of itself. For example, 0.01, or 0.001, or 0.0001 all have 1 significant digit associated. The zeros between the decimal place and unity do not contribute to the significance. When a number is expressed with a decimal point, the zeros to the right of the last non-zero significant digit become significant. For example, 0.10 has 2 significant digits. 0.100 has 3 significant digits. 0.1000 has 4 significant digits. And lastly, when a number is expressed without a decimal point, the zeros to the right of the last non-zero significant digit may or may not be significant, depending upon the previous mathematical operations or designations. For us to designate the proper number of significant digits, the last significant digit is underlined. For example, 500 with an underline for our first zero indicates that this has 2 significant digits associated with it, whereas 500 with no underline only has 1 significant digit. 500 with a period after our last zero has 3 significant digits, and 500.0 has 4 significant digits. Lastly, we can use scientific notation to help in specifying our significant digits. When we use scientific notation, there exists a placeholder, which leads our trailing digit, in which Rule 4 applies. For example, 48.0 e to minus 9 has 3 significant digits, whereas 48 e to minus 9 only has 2 significant digits.